This is the video supplement for the article Correlation and Relativistic Effects in Uranium Metal and Uranium Zirconium Alloy, Validation of Ab initio Approaches, published in the journal Physical Review B. This video is presented by Xiong from University of Wisconsin-Madison. As the title suggests, the material we studied are uranium metal and its alloy with zirconium. Why are they useful materials? Well, they are the primary constituents of our promising fast-reactor metallic nuclear fuels, uranium, plutonium, zirconium, M, where M stands for neptunium, americium, and curium. Previous research have shown that metallic fuels has advantages in performance, economics, and safety over oxide fuels. However, due to the radioactivity and toxicity of such materials, experimental studies are difficult and expensive, and we approach the issue with ab initio modeling. We modeled all the currently known stable solid phases of the uranium metal and the uranium zirconium, as can be seen from the temperature-pressure phase diagram of uranium metal on the left, and the temperature composition phase diagram of uranium zirconium alloy at ambient pressure. There are 3 solid phases of uranium metal: alpha uranium, beta uranium, and gamma uranium, and 5 solid phases of uranium zirconium alloy: alpha uranium alloy, beta uranium alloy, gamma uranium zirconium alloy, alpha zirconium alloy, and delta uranium zirconium alloy. Let us first look at the energetics from DFT GGA. Here we plot the enthalpy formation reference to alpha uranium and alpha zirconium elemental metal phases for alpha uranium alloy, beta uranium metal, beta uranium alloy, alpha zirconium alloy, and delta uranium zirconium alloy. We compare DFT results to those from 3 different CAFA models. These CAFA models can be considered as established representation of experimental data, as they are determined by fitting to experimental phase boundary. It is apparent that DFT enthalpies are much larger than those from the CAFA models. For most phases, more than twice as large. For the case of delta uranium zirconium alloy, DFT GGA predict the wrong sign for the enthalpy formation. These results suggest that DFT GGA does not give sufficiently accurate enthalpy for uranium and uranium zirconium. To improve our theoretical predictions, we use the DFT plus U method for our study. In this slide, we show DFT plus U energetics as function of effective hub U parameter and compare them to CAFA values and or available experimental data. Note that DFT plus U calculations using effective hub U 0 is simply just DFT. Again, we give enthalpy formation for alpha uranium alloy, beta uranium metal, beta uranium alloy, alpha zirconium alloy, and delta uranium zirconium alloy, along with the cohesive energy of alpha uranium metal. We see that DFT plus U enthalpy versus effective hub U are generally V-shaped curves. That is, enthalpy first decreases and approach reference values from CAFA or experiments. Cross the reference value lines approximately between 1 and 1.5 eV. Afterwards, the enthalpy increases. We see that for most cases, the spin-out coupling effect is not large, about 0.02 eV per atom in enthalpy when U parameter is less than 1.5 eV, which we believe is the maximum empirical effective U that is approximate for uranium and uranium zirconium systems. To further determine U effective for uranium and uranium zirconium, we show on the left the theoretical hub U evaluated using the linear response approach for all the known stable solid phases of uranium and uranium zirconium, plotted as functions of composition. We see that they range from 1.9 to 2.3 eV. On the right, we show the root mean square error for ab initio enthalpies plotted as function of U effective. The curves are also V-shaped and have a minimum near U effective equals 1.24 eV. This is within the empirical U effective range of 1 to 1.5 eV seen from the previous enthalpy plots. The two figures show that theoretical U's are approximately 0.8 eV larger than empirical U's, reasonably close but not the same. This is expected since DFT plus U is based on the Hartree-Fock approximation, which is known to overestimate spin and optical polarization, and hence requires a smaller empirical U effective to compensate. It is also clear that Haber U is dependent on composition and structure, so using single U effective for multiple phases is an approximation. It is also necessary to check how the electronic structure changes with U effective and whether it is consistent with enthalpy results. For this purpose, we show the calculated density of states for alpha uranium at various U effective and compare them to experimental XPS and BIS spectra. Note that the experimental spectra have been properly normalized, so the dots and the spectra's magnitude can be compared, in addition to the energy positions of the electronic states. The XPS and BIS spectra show that the valence bands of alpha uranium have three major peaks, which were labeled in our paper as peak 1, A, and B respectively. We found that at effective U equals to 0, the dots reproduce these three peaks, but show two differences. One, peak B splits into two subpeaks. Second, below Fermi level, our calculated dots show another peak near minus 1.3 eV. At U effective equals 1.24 eV, we find quantitative improvement in both the peak magnitude and position. As we further increase U effective to 2.49 and 3.99, the calculated dots is in clearly worse agreement with the experimental spectra. The major and minor spin channel are also no longer degenerate, suggesting the emergence of magnetic moments, which are unphysical. Overall, the electronic structure results are in agreement with the enthalpy in that DFT plus U with a small U effective of 1.24 eV can provide some improvement, while DFT plus U with larger U effective will deteriorate the calculated dots. In summary, we have shown that enthalpies for uranium and uranium zirconium are overestimated by about 0.1 eV per atom when using only DFT, while DFT plus U with U effective near 1.24 eV can reduce this error to about 0.02 eV per atom. The effect of spin-orbit coupling is found to be small for the uranium and uranium zirconium systems. Empirical U effective for U and U zirconium systems are 1 to 1.5 eV, while theoretical U are 1.9 to 2.3 eV. They are reasonably close but not the same. Finally, we show that the electronic structure results are consistent with energetical results, with the density of states showing good agreement with experimental spectra at U effective equals 1.24 eV. We encourage you to read our paper for more detailed results and discussions. Thank you for viewing this video supplement.